Our next speaker is Jay, who is a third-year PhD student at UIUC, advised by Deepak Vasesh. His research interests are in wireless and satellite networks and sensing. Jay, go ahead.
Thank you for the introduction, and hi everyone, I'm Jay from UIUC, and today I'm here to talk to you about our work on improving privacy against wireless sensing. In the last few years, wireless sensors have become a tremendous tool in helping us analyze and monitor human motion. These sensors typically work by sending signals over the air and measuring the reflections off of humans moving in the environment. These sensors can work in non-line of sight and can track your movement through walls, allowing them to see from outside your house when you're going to water your plants, when you're getting a snack at the kitchen table, and even when you're using the bathroom. What's really interesting about these sensors, though, is that they've become so sophisticated and can measure even the smallest of human motions. And this has allowed them to gain insights into other aspects about your health based on movement, such as your sleep, breathing, and even your emotion. Because of all these different functionalities, though, these wireless sensors are now starting to become more and more prevalent. For example, I can buy one of these wireless sensors from a company like TI for only about a couple $100, completely off the shelf. Also, large companies like Google and Amazon have started to embed these wireless sensing devices in their common home IoT devices like Amazon Alexas and Google Homes. Now, all this different sensing functionality is great, but if we take a step back and think about it, in the wrong hands, an eavesdropper can potentially exploit these wireless sensors to steal very private information about your movement without you even knowing that it's happening. Imagine if a burglar has access to one of these devices. They can figure out whether you're in your home or not, or whether you're sleeping, figuring out the perfect time to break in and steal your valuables. Imagine if Google and Amazon had these technologies inside their devices. They could steal private information about your movement and sell it to other companies at the expense of your privacy. And also imagine if healthcare providers forced you to place these devices inside your house so that they could monitor your private health metrics and price your insurance plan based on the private information they collected. What's really frustrating about this problem, though, is that it seems like no matter what we do or how we move, RF signals will always be reflecting off of our bodies. And that makes the problem of hiding our motions from these sensors very challenging. As a result, today, RF privacy is very limited. One solution is to potentially jam the spectrum, and this would prevent these RF sensors from working. But there are two main issues with this solution. First, jamming is very easily detectable by the eavesdropping RF sensor, and this could prompt them to move to a different part of the spectrum to initiate a counterattack. Also, jamming also affects friendly devices inside your house. So things like Wi-Fi and other friendly wireless sensors that you actually want working will be interfered when jamming is initiated. Also, another possible solution is to erect a huge Faraday cage around your house, preventing RF signals from coming in. But as you can see, deploying something like this would be really expensive and impractical. So now this brings us to the main question of our work. What is the more efficient solution to ensure privacy against these wireless devices? To answer this question, we decided to take inspiration from one of the greatest movies of all time, Home Alone. Specifically, I'm talking about this scene, where Kevin basically creates these fake humans moving around his house. And basically, this makes it look like his house is really crowded, and that prevents the burglars from breaking in and trying to attack a 5-year-old kid. So this is the solution right here. All we have to do is have a cardboard cutout of Michael Jordan, put him on a train, and we're good to go. But in all seriousness, what if I told you that doing something like this is actually easier than it looks? And that's what I'm here to talk about today. Today, I would like to present our work, RF Protect, a novel data injection mechanism that helps preserve privacy against wireless sensors. The big idea behind RF Protect is that we can create these fake ghost trajectories in the environment that move around just like real humans. And the advantage of adding these ghosts is that they basically look like fake humans, and they dilute the amount of real human information being sensed by the wireless device. So the question is, how to enable such a phenomenon? Well, the way it works is the wireless sensor basically transmits a signal inside the building to measure who's moving in the environment. And our device, RF Protect, picks up this signal, injects the components required to create these ghosts, and then reflects it back to the wireless sensor, kind of like a backscattering device. Now, the natural follow-up question is, what are we exactly doing to the signal in order to create these ghosts? So we basically need to answer two major research questions. The first of them is, how do we generate these dynamically moving reflections with only a static reflector in the environment? And the second is, once we figure out how to create these reflections, how do we make the movements of these ghosts look more like humans? To get a better understanding of how to spoof these ghosts, we first need to understand how wireless sensing works. So essentially, the idea here is these sensors can localize a victim in a 2D space. And they use something called FMCW ranging to get the distance of the victim with respect to the sensor. The idea here is that the sensor transmits a signal which reflects off of the victim moving in the environment, and that signal comes back to the wireless sensor. Now, by measuring the time of flight between the original signal and the reflection that was received at the sensor, we'll effectively be able to measure the distance of the victim with respect to the wireless sensor. And that is basically calculated using this equation that relates distance to the speed of light by the time of flight of the signal. So now we have the distance, but to get the angle of the victim with respect to the wireless sensor, the sensor is basically augmented with an antenna array. And by modifying the phase at each of these antennas, we can essentially collect the different powers across all the angles when we sweep and figure out where the predominant power is in order to figure out the angle of the victim. So we got two perspectives that we need to attack: the sensor's distance and their sensor's angle perspective. So let's start with the distance. Now, if you remember from the previous slide, the distance is calculated using the time of flight between the original signal sent and the received reflection. Now, because of the unique characteristics of the waveform generated by these wireless sensors, this time of flight actually boils down to a frequency shift between the original signal and the reflected signal. So our key insight here is that if we can modify this frequency shift, we'll effectively be able to change the corresponding time of flight and distance measured by the wireless sensor. So the way it works is RF Protect essentially takes this wireless sensor signal, passes it through an RF switch that turns on or off at frequency f prime. Now, by modulating the signal at different frequencies, we'll essentially be able to create the ghost moving at different distances with respect to the wireless sensor. So now that we created distance spoofing ghosts, we can create ghosts that move along a single axis, kind of like this. But you know what? A more sophisticated ghost, or a real human, would actually move in a much more complicated manner. And what we really need here is to also spoof the angle perspective of the wireless sensor. To do this, we create a physical spread in space. RF Protect uses a 1D panel of antennas, which we deploy against the wall of the building that we're trying to protect. The way this works is actually quite simple. All we do is, for every angle that we want to spoof a ghost on, we simply reflect the signal back on the corresponding antenna related to that angle. For example, if we want to spoof the ghost at the position at the green circle, all we have to do is first collect the signal, add our distance spoofing by modulating the frequency, and then reflect the signal back to the eavesdropping sensor on the antenna circled in green. So now that we figured out how to spoof these wireless sensors and create these dynamically moving reflections, we need to figure out how to make these ghosts move like humans. So the simplest thing to do here would be to have a ghost that moves in a motion like a circle and keep it oscillating on and on again. But the problem here is that this is really easily detectable to the eavesdropper. So what we really want is a ghost to move exactly like a human. To do this, we leverage machine learning, specifically a generative adversarial network. The goal of our GAN is to create a distribution of fake motions that match that of real human motion. But the problem in practice which we found is that traditional GANs suffer from something called modal collapse, where they basically can't output a diverse set of synthetic fake motions that resemble that of real human motion. So the way we fix this problem is that in RF Protect, we use something called a conditional GAN architecture. The way it works is it takes in a noise vector and a set of range labels as conditioning input that help guide the latent space of the model. Therefore, after these inputs are taken, our generator can output a set of synthetic trajectories. Afterwards, we sample a collection of real trajectories, which we got from our collected data set, and we feed both the real and fake trajectories into a discriminator, which tries to classify the trajectories as real or fake to improve the training process. So we have these ghosts, and we can spoof them all around, but how do they help ensure privacy? Well, there are a couple of major scenarios where RF Protect is very helpful. The first is the occupant detection scenario, where we have a burglar trying to figure out if somebody is inside the house. So RF Protect can always spook these fake ghosts or fake humans, making any sorts of occupant detection scenarios deterred. Next, imagine if a snooping neighbor is coming by to see how many people are in your house or trying to do some sort of crowd counting scenario. Because RF Protect can spoof multiple ghosts, any sorts of attacks that try to incorporate crowd counting won't work because RF Protect can always change the number of people seen in the environment. And lastly, imagine when the adversary wants to detect information about your private health metrics. To fight against this problem, RF Protect carefully crafts our ghosts such that they move exactly like real humans, even to the level of breathing, which is where most of these private health metrics are inferred from. So now we evaluate RF Protect by implementing the system end to end. We start by building a common RF sensing-based design, and our design operates in about the 6 to 7 gigahertz frequency range, which works in non-line of sight. We also implement standard post-processing algorithms that are common of the design, like background subtraction and trajectory smoothing to improve the measurements. We experiment in 2 commonly private indoor environments, a home and an office setting. And in both these settings, RF Protect and the wireless sensor are in a realistic non-line of sight environment from each other. The green dot on this figure represents the RF Protect deployment, and the red dot represents the wireless sensor. In each environment, we have our machine learning model generate 45 trajectories, and we have RF Protect spoof these trajectories and see what the wireless sensor measures. So let's see RF Protect in action. So on the right-hand side, you have a wireless sensor heat map, basically showing how a person is moving. And then on the left, you have the corresponding video of what's actually happening. Now you see the person moving around, but as he leaves, the red dot also moves out of the picture. But as soon as he turns on RF Protect, even though there's no actual human in the environment, this red dot is coming back and moving. And this is essentially the ghost moving just like a real human would to protect your home. So now, let's look at the main result of our work, the spoofing error across all 90 trajectories we generated. On the x-axis here, we have the spoofing error in meters, and on the y-axis, we have the CDF. This blue curve represents the set of experiments done in the office, and the orange one represents the set of experiments done in the home. The median spoofing error for the home experiments is about 12.7 centimeters, and the spoofing error for the office is about 24.5. Now, what's really interesting here is that the natural resolution of the radar we designed is already about 15 centimeters. And given that our spoofing errors are so close to that number, this basically implies that any error from spoofing from RF Protect would look like nothing more than a natural imperfection in the radar resolution. We also wanted to demonstrate the trajectory generation capabilities of our machine learning model. And to do this, we use a metric called FID score, which basically compares the distance in distribution of real trajectories to that of the synthetic trajectories. And what we find here is that RF Protect's model has the closest FID score to that of the real data set. And it outperforms all the other trajectory generation baselines which we compare against. We also conducted a 30-person qualitative survey and found that, in general, people couldn't figure out which trajectories were real and which ones were from the ghost. We also wanted to show a result from breathing. And even though we couldn't get into the details of how RF Protect makes our ghosts breathe, we wanted to show you the profiles. The blue profile represents the breathing of a human, and the orange represents the breathing of a ghost. And as you can see, the two are very similar. So ultimately, RF Protect proposes a novel privacy mechanism against wireless sensing. And it does this by creating these ghosts in the environment that move around just like real humans. Although RF Protect takes a very important first step to improving privacy, privacy is in general an arms race. As we create new defenses, the adversary is going to figure out how to improve their attacks. And there are a lot of interesting opportunities for future work here. For example, we can extend RF Protect to actually spoof a 3D threat model where the height of a victim is also being spoofed. Also, these RF sensors are now, instead of not just localizing people, they're also starting to image people as well, and modifying and extending RF Protect accordingly against this imaging sensing type scenario is something that we consider as well. In the future, we envision that RF Protect, because of its natural wall-like deployment, can become a vital part of smart surface work. And if you're interested, I encourage you to check out the code and experimental data sets at the GitHub below. Thank you.
Questions?
And yes, questions. Wenqing Shao Huawei. Is the result of the spoofing is always additive in the sense that you add more human beings, kind of, or perception of more human beings in the room, or can it kind of cancel, kind of remove?
Yeah, that's a very good question. So right now, RF Protect only adds more human beings. And the reason for this is because the way we're modifying the FMCW signal, we're essentially injecting new frequency components and changing the angle of the received, changing the angle sent back to the wireless sensor. And because of the methodology that we're using, the ghosts are pretty much only added. They can't cancel out real human motion.
Yeah, I have another question in the sense that maybe it is just me not kind of having a clear view of the little demo that you're showing. It seems that when you were spoofing, the signal-to-noise ratio is much better than you were doing normal kind of human being detection, because that gives the impression that, okay, I'm proving, letting you know that people can tell that you're spoofing to a certain extent, such that you actually hide whatever is happening inside, right? In the sense that you don't really have to fake human beings to realize the spoofing effect, just telling people, yeah, I'm spoofing. So what you see is not really what's happening inside.
Yeah, so in terms of the signal-to-noise ratio, as you mentioned, in our prototype, we pretty much only use a standard amplifier and don't really consider the power or the SNR received at the wireless sensor as much. But it's something that's very easily extendable to our work, where we can have a dynamic sort of amplifier reflecting the signal back at the wireless sensor. And we can incorporate SNR as one of the different metrics as part of our machine learning model to better tune the SNR that is basically seen at the received wireless sensor.
Okay. Suman?
Oh, thank you. Shuman Banerjee from Wisconsin. Great talk and very good presentation. I had a question about how this is used. So you're adding these fake humans or ghosts. So is it not the case that the attacker can basically see an actual human and some ghost, but I still learn about the human, right? Is that you're not like if you're detecting a person's breathing and you have the heart rate or other data, you see some person, you think there is a fake, but you don't know that person's fake, but you still get the data of the human, right? So is that that's still some loss of privacy. Did I get that correct?
Yeah, so that's exactly correct. So basically, the thing with RF Protect is you're adding these ghosts. You can't exactly hide the human from the wireless sensor because that would require most of these limited solutions where you're like jamming the whole spectrum. But what's really interesting about this sort of data injection type attack is that it's found to be really effective in other sorts of communities, like web privacy, for example, where people are trying to infer a profile of a user based on clicks and queries to a web server. Now, you can't exactly hide those queries, but what's interesting is they also do a similar sort of data injection mechanism where they have a bunch of fake queries to hide the exact profile of a user, and that's basically the same approach that we're trying to take here.
Okay, let's thank the speaker again. Thank you, Jay. Okay.